Believe it or not, we're up to section 11.2, the very last textbook section of the semester. My gosh, how time has flown. Let's start out this lecture with a motivating example, and then we'll generalize it a little bit into a more abstract discussion before we come back to solving the problem. All right, so the motivating example is about COVID rates and vaccinations. Some real-world applications here. The following contingency table represents Bogodovia's COVID statistics for December 2021. And by the way, I might point out that there is no such country as Bogodovia. I've made it up for this example. This table represents 10,000 residents of Bogodovia who contracted COVID-19 that month. Now, when we look at this table, we see that the patients in this table are being categorized in two different ways. First, by COVID outcome, and second, by vaccination status. So each outcome represents a column of this table. There are three of them. Some patients were hospitalized, but recovered in the hospital. Some patients died, and some patients recovered at home, never having gone to the hospital. And if we look at the row variables, or categories, I should say, we're breaking the patients down into those who were unvaccinated versus those who were vaccinated. And I believe we've seen contingency tables a little bit early in the course. So, for example, if you look at a number like this 92 here, that represents the number of individuals who are both in the death column and the unvaccinated row. So, in other words, those are the unvaccinated patients who died. Okay, the question is, do COVID-19 hospitalization and death rates, the columns, depend on vaccination status? The rows. Do the columns depend on the rows? So, for example, you might note that the numbers in the bottom row are all smaller in the vaccination row. The numbers in the bottom row are all smaller than the numbers immediately above them. But that's not indicative of a proportion. It's just telling us that there are fewer vaccinated people than unvaccinated. So the real question is, are these rows proportional to each other? Or are they disproportionate in some way? And if they're disproportionate, that indicates that the hospitalization and death rates depend somehow on whether the patient was vaccinated. All right, let's generalize this a little bit. Let's abstractify it. So the overview here says, in this section, we will categorize a sample in two different ways, like health outcome and vaccination status. And we will run a test to see whether those two categorizations seem to operate independently of each other or whether there seems to be an interaction between them. So the technical word that we're introducing here is independence. That's why this section is called Test for Independence. So the data is summarized in a contingency table like the one we just looked at, where the first variable is broken down into column categories. The second variable is broken down into row categories. Theoretically, we can have as many column categories and as many row categories as you want. And that fits in with the theme of this chapter, which is multiple variables, random variables. Another point that I make here, I'm going to come back to this point last. So let's go ahead and work through this example, the one that we've seen first. All right, so how do we set up a hypothesis test? The question, as stated in plain English, again, was, does the outcome of the first variable depend on the outcome of the second variable, or vice versa? So the null hypothesis is the one that uses the null or the not. The null hypothesis says, nope, the row and column variables do not depend on each other. And if that's the case, that would mean that the rows are all proportional to one another. And likewise for the columns. The columns would be proportional to one another. Alternately to that, the alternate hypothesis would be just the opposite. The row and column variables do depend on each other. And if that's the case, then the different rows actually represent different distributions. And so do the columns. Okay, so how do we answer the question? We set up a null hypothesis and an alternate hypothesis, and then we know the routine from here. We need a critical value as a cutoff number, which we can find before we even look at the sample. And then we're going to actually look at the sample, get a test statistic out of it. And if that test statistic exceeds the critical value, we are going to reject the null hypothesis. Likewise, if that test statistic is larger than the critical value, then it cuts off a smaller tail. So its p-value is smaller than the significance. Now, as it turns out, for this kind of test, we always run a two-dimensional test with a p-value. The test statistic turns out to be chi-squared again. And also, once again, we don't really need to worry about how that chi-squared distribution is actually related to the contingency table. That math is beyond this course. But just take it on faith that there is a chi-squared distribution that describes this problem. And when we run StatCrunch, at least for this class and these homework problems, we are going to be analyzing it with the p-value. Okay, so what do we do on StatCrunch? The sequence of steps is given here. Stat, tables, contingency, with summary. Okay, let's take a glance back at this example again. I've given you some sample problems here to think about. Here, this one says state the hypotheses. So I hope you remember the null hypothesis says that the row and column variables operate independently of each other. Now, we need to be clear when we write these hypotheses that the wording that we use needs to refer to the row and column variables, not the categories. That's a little bit of a subtlety, but that's the point I'm making here. It is helpful to create row and column headers broader than the categories. These are the two variables to be used in the test. In this example, the variables are given to us. Here is the column variable. It's called COVID outcome. And here is the row variable, and it's called vaccination status. So in our null hypothesis, we don't want to be using these categories. We don't want to be using hospitalization or vaccinated in the null hypothesis. We will say the COVID outcome is independent of the vaccination status. And then, of course, the alternate would be that they do depend on each other somehow. Okay. All right, get the test statistic chi-squared and its p-value from StatCrunch. So here's the same table. Up here we have these three columns have the column categories: hospital, death, and basically minor illness. And then the row variables. The row variable is vaccination status, which can be either unvaccinated or vaccinated. So the one thing that's not stated in this table is the column variable. It says vaccination status, but up here it doesn't say outcome, right? So we go through these steps that are outlined in the lecture notes. Stat, tables, contingency with summary. It says select the columns. What it means here is select those column categories. Vaccination status is not one of them, right? The column categories were these three: hospitalized but recovered, died, or minor illness, recovered at home. So those are the only three column variables. Again, I'm holding down the control button to select all of them. And then it asks, this part is a little bit weird. It says, where do I find the row labels? Well, the row labels are here, unvaccinated and vaccinated, and they're in this column that's called vax status. So, and that's what we're looking for here. That's basically the row variable. So I have to admit, it's a little bit strange the way we enter things here. There's a row variable. The row variable is identified here above its categories. But for the columns, we have the categories but not the variable. So that's just how it is on StatCrunch. Okay. And then I guess we just click compute. And we get this readout. And what we look for down here is the chi-square test. So this tells us that the value of the chi-square variable is 44.02. So I'm going to enter that here. Chi-squared was 44.02. Its p-value is also given in the readout. It says less than 0.0001. Very small. P-value is less than 0.0001. Okay, so now we get to compare P to alpha and make our conclusion in plain English. Notice that this problem didn't indicate a level of significance. So we're going to go ahead and use the default here, which is 0.05. And how does the p-value compare to that alpha? You can see that it's p is much smaller than alpha. And when the p-value is smaller than the significance alpha, that indicates that we conclude the alternate hypothesis, right? We reject the null hypothesis. So in English, that means, yes, the COVID outcome does depend on the vaccination status. Remember that when it comes to concluding the null or alternate hypothesis, we usually are always kind of being mindful of the burden of proof. So we assume the null hypothesis unless it's proven beyond a significant doubt, which in this case it was. So we word it like there is sufficient evidence to reject the null hypothesis. Or, in plainer English, the COVID outcome depends on the vaccination status.